Hello, everyone. My name is Yang. I'm currently a postdoc researcher at the University of Illinois, Urbana-Champaign. So it is my great honor here today to present our recent work on developing a crowd-guided neural network hyperparameter optimization approach in the AI-based smart urban sensing applications. So here, we first introduce some background of the applications that we worked in this paper. So motivated by the state-of-art ambiguous and pervasive sensing platform and the advanced AI models, smart urban sensing has emerged as a powerful sensing paradigm to capture a rich set of information of the urban environments at an unprecedented scales for the smart city management. So in this paper, we focus on these AI-driven smart urban sensing applications. In particular, the recent advances in AI has transformed many important domains of urban sensing, and we expect its enhancement is going to be intensified. So for example, the Crowdworks have developed this deep learning model to automatically monitor the structural health conditions of the citywide infrastructure. So in this paper, we focus on the hyperparameter optimization in the ASUS applications. It is observed that the configuration of the hyperparameters plays a key role in the AI model's performance. So for example, we noticed that even a single hyperparameter change in terms of epoch or the learning rates of the AI model could cause the AI models to make completely different and inaccurate estimations. So however, the hyperparameter in current ASUS solutions are often manually configured by the AI specialist, which is known to be both error-prone and suboptimal. So motivated by the above limitation, we study a hyperparameter optimization problem in the ASUS applications. So our goal here is to automatically identify the optimal hyperparameter configuration for an ASUS model without the manual inputs from the AI specialist. So on the other hand, we noticed that the human intelligence is often more reliable in estimating the physical status of the urban environment compared to the AI model of different hyperparameter configurations. Therefore, we can leverage such human intelligence to infer the probability that a given hyperparameter configuration makes the correct ASUS estimation, and then select the optimal one that can produce the best ASUS performance. So motivated the above observation, we developed a crowd AI collaborative learning framework by utilizing the human intelligence from the crowdsourcing system to identify the optimal hyperparameter configuration for an ASUS model. In particular, our design is focused on enable the user can use our CrowdOptim to perform the ASUS tasks in 4 steps. So first, the users can choose upload a set of the urban sensing images. And then the user can start the crowd query to acquire the human intelligence from the crowdsourcing systems to get the search of the optimal hyperparameter configuration. And third, the users can start the hyperparameter optimization process, where our CrowdOptim leverages these acquired crowd labels to identify the optimal hyperparameter configuration. Finally, the CrowdOptim can generate the estimated crowd label for each uploaded images using the identified optimal hyperparameter configuration. So in general, the CrowdOptim contains 2 key modules to perform this crowd-driven hyperparameter optimization tasks. So first, we have the CHST module that designs a crowd-manageable hyperparameter space transformation model that effectively reduces the hyperparameter search space through a novel resource-constrained multi-armed branded learning model design. And then we have the COHI module that develops a principled crowd AI collaborative estimation model that leverages the imperfect crowd intelligence to get the selection of the optimal hyperparameter configuration from the reduced search space identified by the previous module. So in the first module, we actually observe an interesting one-on-one mapping between our CHST program and this budget-constrained MVP program. So in the budget-constrained MVP program, An agent aims to identify a subset of machines with the highest winning probabilities from a large set of the candidate machines, given a budget constraints. On one hand, the agent would like to spend money on trying the new machines. On the other hand, the agent would like to keep playing the machines that already return a high reward in order to maximize the overall profit. Similarly, in our CHST program, our goal is to select the reduced search space from the original search space, giving a finite amount of computational time. We have to balance the exploration of the new hyperparameter configurations and the exploitation of keep tuning the selected hyperparameter configuration, which already returns the best ASUS performance. Then in the second module, we developed a novel core-driven hyperparameter optimization model to effectively leveraging the imperfect core intelligence to identify the optimal hyperparameter configuration from the core manageable hyperparameter search space generated by the previous module. So in our model, we consider both hyperparameter configurations and the core workers as the data sources with this unknown optimality that makes their estimations on the images of unknown class labels. We then introduce a novel called AI collaborative estimation framework to estimate the optimality of each hyperparameter configuration in order to identify the optimal ones through the maximum likelihood estimation. In our experiment, we evaluated the performance of the CrowdOptim framework through two real-world smart urban sensing datasets, which are the smart city infrastructure monitoring and the urban environment cleanliness assessment. So, in both applications, the physical status of the urban environments has been classified into 3 different classes. We show an example of our evaluation results, where we vary the ratio of the studied images that are sent to the crowdsourcing systems to collect the crowd labels. And we also compared our CrowdOptim with a rich set of AI and hyperparameter optimization baselines. So for example, this hybrid is a representative hyperparameter optimization approach that utilizes this non-stochastic and infinite armed branded-based mechanism to ensure this effective neural network optimization process. And finally, we observe that our scheme consistently outperforms all compared baselines with the best ASUS performance. So the performance gains of our scheme mainly achieved by this effective core-driven hyperparameter optimization design that addresses this bias and inefficiency of the manual neural network hyperparameter configuration process by exploring the collective wisdom of both core and AI. So that's conclude my presentation. Please let me know if you have any questions. Thank you.